do that was because you guys, we had that brief 2 weeks or so that we really kind of hit it hard, right? Okay, so you're reaping the benefits of that. All right, so putting it all together, we are now on page 591. Putting it all together. So let's go ahead and flip to page 592. It tells you the green box there, go ahead and read that. That is very similar to what we learned in the one-sided versus two-sided when we talked about the population proportion. This is now going to the mean, the same exact stuff. Okay, so let's do the example where the healthy streams. The level of dissolved oxygen in a stream or river is an important indicator of the water's ability to support aquatic life. Researcher measures the dissolved oxygen level at 15 random chosen locations along a stream. Here are the results in milligrams per liter. And it gives you 15 things there. An average DO of the dissolved oxygen level below 5 puts aquatic life at risk. Okay. Do the data provide convincing evidence that at alpha is equal to 0.05 significance level that aquatic life in this stream is at risk? Okay, so what are we looking for here? What is my ho and what is my ha? Hmm? Never mind. So the ho would be, it is the dissolved oxygen is at 5, right? Whereas the ha would be is less than 5. We want it to be greater than 5, right? Actually, is it greater than 5? We want less than 5. Less than 5 would be what? That's not good, right? That's not good, right? Look at the data. What does it look like?
8 of them are
No, they're pretty convincing. There are quite a few of them that are less than 5, right? So this is what we're suspecting. We're suspecting this. So this is what we're going to try to disprove here, right? Okay, and the alpha was what? 0.01. Was it 5? 5. Easily fixable. A, okay, no. So what do we need to do? So this is our state, right? This is the state. And then we're going to do the plan. What's our plan? What do we have to do in the plan? Check the conditions. So yes, it is a random sample. They said it was randomly selected 15 places. 2, you have to check that n is, well, this obviously makes sense, right? Because you could do infinite amount of places to randomly select it from, right? Okay, so it's going to be less than 10. 3, large counts. Does it satisfy the large counts? Not immediately, right? Because it's less than 30, right? So we need to do a dot plot, right? We need to do a dot plot. Or the book actually did a histogram, it looks like. On the histogram, if you look at page 593, peek and cheat there, you see the histogram there. And it looks pretty symmetric. There's no skewness there, right? Doesn't look like there's any outliers either. So we're going to call it good. We're going to call the large counts good. Let's actually do this. So if I on the do, what do I need to do? Dang, stupid guys didn't give you the X bar nor the standard deviation, right? So how are you going to find it? Stat ed, go ahead and input the L1, right? Let's do it. You put it to L1.
Yeah, calculator.
Didn't bring your calculator.
I didn't bring a pencil.
Oh, you did bring it. Normally I would say scoop together and do it together, but we can't do that, so. So we do L1 and L2, and we're gonna find that X bar is something and the standard deviation is something. So. Shout it out once you found it.
X bar is 4.77
Uh-huh.
and the standard deviation is 0.9396.
Anybody come up with anything else? Any different? You good? Found the same thing? Kaden,
I'm in.
you're confused. What
I
else is
forgot how to
new?
put it in. Like I got it on the L1 and I forgot what the press.
Stat, Cal, one of our tests. Okay. So we have verified 1, 2, 3. Okay, 4.
Where'd you get one?
Okay.
I looked in the book and yeah, we might.
You got it right? All right, so the book is correct. We're not correct because we know that we're correct. The book is correct, right? Okay, so we define this, right? 4.77 minus 5. This guy, 0.9396, square root of, what was n? What do we get? I just want to make sure the book is correct. Okay, that's what the book says. So the book is good, since we are always going to be good. So so this is 0.94, so, and it's on the less, so we are here. And this is 5, 4.77. Okay. So what is that number? Somebody find it using the calculator. You'd use the TCDF, right? TCDF. I go from 0 to 4.77 or 4.77 and 5. Okay, so TCDF, you go with TCDF, the first one you're gonna put in is negative 0.94, no, 0, and negative, not 0, negative 100, negative 0.94 with a 14 degree of freedom, right? Degree of freedom is 14. What? Point,
1816.
everybody else got that? Same one, 0.1816. The book says 0.1816. Okay, we're good. So what's my p-value? What's my p-value? 18.16%, right? 18.16%, right? And we're going to compare that to 5%. The p-value is greater than alpha. Darn it. That means that we failed to reject. We failed to reject this. We do not have convincing evidence that this is true. Okay. Given your conclusion in part A, what kind of mistake, a type 1 error or type 2 error could you have made? Ooh. What kind of error could I have made? So I failed to reject, right? So if I was supposed to reject, that would be a type 1 or a type 2. Type 1, right? So is that, hang on. There we go. Because we failed to reject O in part A, we could have made a type 2 error. Failing to reject the whole when the high is true. Okay? See, does that make sense to you guys? Because if I got the incorrect p-value, right? If I did this, if I got an error, right? And the p-value was supposed to be lower than alpha, right? But it actually came up positive or higher than alpha, right? Which means that I was supposed to reject, but I failed to reject. So that's type 2, right? Type 2 is where? Where is type 1, type 2? That was on page 9.1, right? Page 560. 560, go to page 560, bottom of page 560. So if the high is true, okay, if the high is true, okay, because it looks like the high is true, right? It looks like it's less than 5, right? So if I'm supposed to, if the high is true and I fail to reject, that is a type 2, right? Type 2, right? All right, so that's that. That was the first one. Now flip the page, and obviously, just like we did with the confidence intervals, we can do the significance testing on your calculator. And it shows you how to do that. So read that. Stat test. So let's go and actually try it on your calculator. You have calculators out. So let's go and see if you can do the one sample t-test using your calculator. And this is the one we just did, right? So your input would be a data, right? And it's a list from L1, but you have it in your L1, right? Currently, right? It should be in L1. A lot easier. However, calculator is only as good as the user, so you have to really understand what you're doing, right? Is what I'm saying, right? All right, that's good. So let's move on to the two-sided tests and confidence intervals. We already did the two-sided tests once, right? We did the very first one we did here was the two-sided test, right? Now let's go ahead and do that again. Let's go to the two-sided test and confidence interval. The link between the two-sided test and confidence intervals for a population mean allows us to make a conclusion directly from a confidence interval. If a 95% confidence interval for mu does not capture the null value, we can reject the whole immediately. And that the mu is equal to mu naught in a two-sided test. If a 95% interval for the mu captures, if it captures the null value mu 0, then we should fail to reject. So let's see how this works. Let's go ahead and do the example there of juicy pineapples. At the Hawaii Pineapple Company, the mean weight of the pineapples. Okay, we've done this. We definitely talked about pineapples, right? Remember way back when we talked about pineapples? What?
I definitely remember the pineapple.
You never remember the pineapples? You're a pineapple guy? Okay, the mean weight from a field was 31 ounces last year. A different irrigation system was installed. Managers wondered if this change will affect the mean weight of, well, to find out, they select and weigh a random sample of 50 from the year's crop. A, state an appropriate pair of hypotheses for significance testing in this setting. Okay, so the whole would be, that mu is equal to 31. The ha was mu is not equal to 31. Remember this? We did do this, right? Okay. So that'll be that. And is there any alpha? There is no alpha, so alpha must be 0.5, 0.05, right? And the parameter of interest. Okay, so 0.05. So parameter is the mean weight of the pineapples, correct? See if that is all they want us to do for A. Yeah, we got that. Mu is that. Okay, where mu is the true mean weight of all pineapples and fruit. Very good. B, check the conditions for performing the test in part A. What are the conditions that need to be met? Random sample, less than 10%. And we're doing 50, right? So I'm assuming there are going to be more than 500 pineapples for that year. Otherwise, you got a problem. You're not selling many pineapples, right? Okay, and then so n is greater than 50. 50 is greater than 30, right? So by the central limit theorem, the large counts is good. Okay, C. A 95% confidence interval for the mean weight of population growing in the year was 31.255, 31.255 to 32.616. Okay. So this was the confidence interval for 95%. So what does that mean? If you look at it, it means that I actually know this now. What is this? What is the middle? I add these two together and divide it by 2, right? That would be the middle, right? And I'm going to guess it's about like 31.9-ish. 31.9. Okay, 31.9. Okay. So here's what they're saying. We did a 95% confidence interval, and guess what happened? The low end here is 31.25. The high end here is 32.616, and I have in here what, 95%, correct? Right? So I don't even have to do the significance testing. I know that 31 is over here. So I immediately say that the p-value is less than the alpha. Right? There's no need to do this if I am given this data here. Okay. Okay, blah, 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 blah. Based on this interval, what conclusion can you make for the test of the hypothesis? Blah, 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 blah. So the conclusion is basically that, oh, there's a D here too. So 31 is not as a plausible value, so we reject the whole. We immediately reject the whole, and we have convincing evidence that it is not 31, right? Okay, and then D, can we conclude that the different irrigation system caused a change in the mean weight of pineapples produced? Can we do that? Oh, why not? There's a lot of things that we're missing here, right? It's not an experiment, right? So it's not a controlled experiment. So obviously, because there can be confounding factors, there can be other things that are going on, right? There, you could have a lot of, I don't know, what kind of wildlife eats pineapple? It had a lot of deer running around eating up your pineapple. I don't know, right? But there are different things that could be happening. Okay. Okay. Okay, it says, yeah, no, this was not a randomized comparative experiment, so we cannot infer, we cannot say that there was causation, right? Okay, so that's good. We're gonna stop right here today.